Welcome to Organic Chemistry. In this video, we explore ethers, the incredibly stable functional group, except in the case of epoxides. Let's get started. Ethers are low-priority functional groups in IUPAC ordering. They behave much more like alkyl substituents or halides rather than like alcohols. And why is that? Because ethers do not have hydrogen bond donors. Their sigma bonds are only weakly polarized. There's no pi system, there's no conjugation, no resonance stability to exploit. It's why ethers sit near the bottom of the functional group hierarchy. Epoxides, of course, are a special case, however, and not because of electronics, but because of its ring strain. Ethers are named as alkoxy substituents. Alkoxy is to ether what alkyl is to a hydrocarbon. So methyl, methoxy, right, and so on. The main chain is still the longest carbon chain, and the ether is treated as a substituent unless a higher priority group is present. Small cyclic ethers get special names. Three-membered rings, oxyrane, like epoxide. Four-membered oxyetane, five-membered tetrahydrofuran, six-membered tetrahydropyran. As the ring size increases, strain drops and stability increases. Outside of such small rings, then, ethers are exceptionally stable. They resist bases. They resist mild nucleophiles. They resist oxidation, and they resist reduction. That's why ethers are some of the most common protecting groups for alcohols. The Williamson Ether Synthesis. This is the primary method for making ethers, and it goes way back to 1850. Step one, we use a strong base, usually sodium hydride, which deprotonates an alcohol and forms an alkoxide. Step two, the alkoxide performs an SN2 attack on an alkyl halide. Key rule, SN2 works best on primary carbons. Primary is excellent, versus secondary, not so much, and tertiary, impossible. So if you want a bulky ether, the bulky part must be the alkoxide, not the electrophile. Ethers are most definitely stable. That is until acid is added. With excess acid and heat, ethers can be cleaved. The mechanism depends on substitution. Primary carbon will be SN2, secondary mostly SN1, and of course tertiary SN1 only. The ether oxygen is protonated first, turning it into a good leaving group. This is why ether protecting groups can be removed selectively with acid. And now we turn to epoxides. Epoxides are formed from alkenes using peracids, most commonly metachloropurbenzoic acid. This reaction is concerted, stereospecific. It adds according to syn addition, same side, superfacial to the pi system. Cis alkenes give cis epoxides. Trans alkenes give trans epoxides. There are no carbocations, no rearrangements. The alkene geometry is essentially remembered in the product. The peroxide O single bond O bond is very weak due to lone pair repulsions. The carbonyl is activated by the electron withdrawing chloro substituent on the benzene ring. The entire reaction is driven by the relief of oxygen single bonded oxygen repulsion and the formation of strong carbon single bond oxygen bonds. This is not brute force. It is an elegant redistribution of electron density. When epoxides, however, are opened under acidic conditions, notice how things change. Step 1, epoxide oxygen will be protonated. And step 2, the ring opens with partial carbocation character. The result is different from what you may have seen previously, that the nucleophilic attacks the more substituted carbon, and the opening occurs anti. The product is a transdiol. In the alcoholysis of epoxides under acidic conditions, we have the same mechanism but a different nucleophile. Under acid, alcohol attacks the more substituted carbon, still anti-opening, and still inversion at the attacked carbon. Even tertiary carbons can be attacked because the ring strain lowers steric barriers. So here we see a tertiary epoxide carbon is not a normal tertiary carbon. Under base-catalyzed conditions, there is no protonation step. This means that this base-catalyzed epoxide opening is pure SN2 character. There is the attack at the less substituted carbon, still anti-opening. Regioselectivity reverses in comparison to the acid catalyzed epoxide opening. So, same molecule, same nucleophile, different conditions, different product. So, in closing, ethers are incredibly stable, very low in reactivity, excellent protecting groups. We see how to form them as well as how to cleave them. And then in the case of epoxides, which are substantially more reactive, we can use acid or base conditions to decide where and how the ring opens. Till next time, Crip.